everyone. So I'm going to talk about the interaction with turbulence. Okay, so yesterday we have seen that you can track particles in a flow, and we did some exercise where there's no flow. Okay, so now we are going to consider a specific flow and a turbulent flow. So it will be involved in the different forces through the drag. So you see here that you have u, the velocity of the flow, u, and you have also u and its derivatives, so temporal derivative and spatial derivatives within the added mass effect. And you have also u, the flow, within the lift force and the vorticity. Okay, so you see that the force balance will be coupled to the flow dynamics through different terms. Okay, so the question is, what will be the effect of turbulence on the dispersion of particles? So if you seed many particles in the flow, in a turbulent flow, are they going to be dispersed everywhere, or are they going to accumulate at some place? Okay. So actually you can sort the different interactions between particles and fluid within a number of categories which are here. Okay. So the first type of interaction is called one-way coupling. Okay, so this is what I'm going to talk tomorrow, today, and then we are going to move forward by making it more and more complex. Okay, so in the first sort of first type of interaction, what is called one-way coupling means you have the effect of the flow on the trajectory. Okay, so you see the particles in the flow, and because of the different forces acting on these particles, they are going to react to the flow. They are going to accumulate, they are going to be dispersed, they are going to move because of the presence of the flow. Okay, so this is a one-way coupling. The second type of interaction is two-way coupling. So it means that now, because you have particles or bubbles or drops inside the flow, they will have a feedback effect on the flow. Like if you take, let's say, some quiescent still fluid and you inject bubbles, like in a sparkling water, because the bubbles are rising, of course, they will entrain the fluid. Okay, so there is a feedback effect of the dispersed phase, bubbles, drops, or particles, on the flow. Okay, so this is two-way coupling. You have one-way coupling, this is the effect of the fluid on the trajectories of the particles, and two-way coupling, you have the feedback effect of the particles on the flow. Okay, so you can, for example, have some modulation of turbulence, you can enhance the turbulence, or you can damp the turbulence, you can modify the drag by injecting particles because they accumulate at some point, and then they will modify the structure of the flow. So this is what is called two-way coupling. So I'm going also to talk about that tomorrow, this morning. Then you have freeway coupling. Freeway coupling is when you start to have interaction between the particles. Okay, so you see that in that force balance, I've never spoke about the presence of another particle. Okay, so this is for a spherical, rigid, small particle, but for a single particle. So you are going, if you use this force balance, you are assuming that if you have many particles, they are going to behave independently. Okay, this particle is moving, that particle is moving, but they don't know each other. Okay, there's no interactions between the particles. So in the freeway coupling, you start to have interaction, because when a particle is moving here, of course it will modify the flow around the surface, and the particle which is close to that particle, they will move because the flow has been moving in between. Okay, so this is freeway coupling. You have trajectories of particles because of the flow. You have the feedback effect of the particles on the flow, but now the feedback effect of the flow is going to modify this particle. Okay, that particle is moving, and this one is going to react because you have a fluid in between. So this is freeway coupling. And then four-way coupling is now when you have really direct interaction between the particles, like a collision. Okay, so when you have many particles, if the flow is if the suspension is very dispersed, so the particles are going to move independently. But now if you start to increase the concentration, you may have close contact between the particles. And if you have a contact, you will have a collision, and of course the trajectory will be different. And this effect is also not accounted for in that equation, because here you don't see any collision between the particles. There's no model for collision. Okay, so for the four-way coupling, you have trajectories, you have the feedback effect of the particle on the fluid, you have direct interaction between the particle through the fluid perturbation, and now we are including the effect of collisions between the particles. Okay, so this is four-way coupling, four different ways of coupling. So this is for dispersed flow, and you increase the concentration when you move from one-way to two-way to three-way to four-way, because as you increase the concentration, the particles are coming closer and closer. So the probability for interaction, the probability for collision is increasing. Okay. And now here you may not see what is written here. So it's dense flow. So dense flow now, instead of having a flow which is dominating by the fluid motion, now the flow will be driven by the particles. So you are coming very close to what is called a porous media, where you have more particles than fluid. So the fluid is moving because the particles are moving. Okay, so now you have what is called collision-dominated flow, and then at some point you have contact-dominated flow, because the particles are so close that they are always in contact with each other, and then the physics is not controlled by the Navier-Stokes equation, by the fluid equation, but it is controlled by the solid equation. And then you have like a porous media, a non-consolidated porous media, which means the particles are moving, but the fluid also is moving because of the motion of the particle. Okay, so when you go across all these families, you go for very, very dilute suspension, so sparse flow. You have few particles in a turbulent flow, so you can make the assumption that they are going to have independent trajectory, so you can track this trajectory with this kind of force balance. Okay. Then you increase a bit the concentration, and you need to account for the effect of the particles on the flow, because they are going to accumulate somewhere, and of course the fluid flow will be modified by the presence of the particles. So this is two-way. Three-way, now the particles are coming closer, so when one particle is moving, the fluid which is in between is also moving, and then the other particle is reacting. Okay, so this is three-way. And now the concentration is even larger, and the particles are coming closer, and the probability for collision is increasing. And then you have four-way coupling, because you have also the collisions between the particles. And then the last two sections are related to very dense suspension, almost like close packing. Okay? So I'm going to talk about this and what is the effect of particles on concentration. I'm going to show you how you can modify the equations of the fluid, the Navier-Stokes equation, to account for the presence of the particles. Then I'm going to talk about this type of interaction. How can we model the collisions between particles, and what is the effect of the fluid, which is in between the particle during a collision. And I'm not going to talk about that. Okay? So we start with what we did yesterday. So you know that based on this force balance, you can evaluate the settling speed of the particle. You know also that this settling speed needs a certain time to establish. Okay, so there is a transient regime during which the velocity is going to increase from 0 to the terminal velocity. And this is based on the rate of acceleration of the particle over a certain time scale, tau p, that we defined yesterday during the tutorial. Okay. So now the question is, if we take a complex flow, so yesterday that was no flow, if we take a complex flow like turbulence, what will be the response of the particles? So I will give you just a brief introduction to what is turbulence. You had some exercise on fluid mechanics, but that I've seen on the book that it was only Poiseuille flow, laminar flow, so you need to know what is turbulence, because it's everywhere in the nature, but also everywhere in industrial processes. So what is turbulence? So this is a picture of a turbulent flow. Okay, so a turbulent flow is something that you get when you take, let's say, a cube of water and then you shake it very intensively. You are going to produce inside that fluid the motion, a lot of motion. Okay, so the fluid is moving in different directions, and you have swirls, you have eddies, you have flow streams. Okay, so it is moving a lot. So here, this is what you see. You see a turbulent flow which is composed of eddies. Okay, all these worms, let's say, are eddies. Okay, so there are eddies which are rotating, and they are moving like this. Okay, and to my students, I'm saying that you can think about turbulence as pasta. Okay, so you have a pasta sauce. Pasta sauce is the fluid, and the pasta, the spaghettis, are like vortices. So they are very intense vortices which are rotating, like a cyclone in the atmosphere. A very strong vortex. So in the turbulent flow, you have the same. So you have pasta, which is the fluid which is around, it's not moving much, and then you have inside that very intense eddies, very intense vortices which are rotating very fast. Okay, and this is what you see here. All these green objects are vortices, okay, which are rotating. Okay, so what we can say to characterize turbulence is to say that it's a very random, chaotic flow, okay, because if you take, let's say, a probe and you want to measure what is the velocity at one point, you will see a lot of oscillation, a lot of fluctuations. Okay, so if I give you the velocity at that point, you are unable to give me what will be the velocity within 1, 2, 3 seconds, because the flow is moving a lot. Okay, so the flow is random, is chaotic, is very difficult to predict. Why is it so? It's because it's extremely sensitive to initial condition and boundary conditions. Okay, so when you have a turbulent flow within a pipe, so you know that the transition to turbulence is at a Reynolds number around 2000, 2500. And why do you get the transition to turbulence? It's because you have small perturbations everywhere. Okay, so you have the perturbation coming from the pump. Okay, so the pump is rotating. There's oscillation within the pump. So you have oscillation in the flow. You have also perturbations coming from the roughness of the walls. Okay, so you have, even if the wall is very smooth, you still have roughness, very difficult to predict, to measure at the scale of 10 to the minus 6 meters. Okay, so very small. And then you have also perturbation coming from the exterior. For example, you have acoustic perturbation. Okay, if I do an experiment within a pipe, and then I'm talking to my colleague, I'm going to send acoustic waves to the pipe, and these acoustic waves are going to shake a bit, very, very gently, but it's going to shake the pipe, and these oscillations are going to be enhanced by the Navier-Stokes equation, and then it will produce turbulence. Okay, so actually a turbulent flow is a flow which is extremely sensible to all perturbation. Perturbation at the initial condition, perturbation at the boundary conditions. Okay, and this is why, so you know that the flow in the atmosphere is at very high Reynolds number, and it is very chaotic, and this is why the forecast is very difficult to achieve. Okay, so if I give you, let's say, over India, the map of the temperature, the map of the wind currents and everything at some point, and I ask you what will be the weather tomorrow, maybe you can make it. Okay, within an hour you can make it. Maybe tomorrow you can make it. But if I ask you what will be the weather within 1 month, within 1 year, you don't have any idea. And it's because although the Navier-Stokes equation, which are controlling the fluid motion at any scale, from the lab scale to the atmosphere, these equations are non-linear because of the U scalar gradient of U. And any perturbation will be increased if the Reynolds number is very high. So when I say to you, I know the flow stream, I know the temperature over India now, it's not true. I know some values of the temperature at some points with a certain accuracy. And any mismatch, any discrepancy will be enhanced by the Navier-Stokes equation and by the nonlinear terms. And all this perturbation, all these fluctuations that you don't know, and that you cannot know because you cannot, measure the temperature everywhere on the Earth. All these perturbations will be enhanced, and at some point you will reach a state within 1 day, 2 days, 1 week, 1 month, which will be completely different from the initial condition. And it's very difficult to predict that. Okay, so this is why the confident time is about 2-3 days when you do forecast prediction. Okay, and this is exactly the same in a pipe. Actually, in a pipe, the flow you can predict what will be the average. Maybe you can predict what will be the RMS, the fluctuations, but you cannot predict what will be exactly the value of the velocity at that point if you run your pipe during 1 hour and then you make another measurement. You are unable to predict what will be exactly the velocity, okay? Because you have perturbations everywhere, the roughness, the oscillations, the pump, and then all these perturbations are going to be enhanced by the nonlinear effect of the Navier-Stokes equation, okay? So the flow is strongly nonlinear, and it is because of the Navier-Stokes equation. Another characteristic is that within a turbulent flow, you have a wide range of length and time scales. So I mean, you have, if you take, let's say, a mixing tank, okay, so you have an impeller, and you are going to generate turbulence into your, because you want to mix some fluids. So you will have vortices which are related to the size of the container or the size of the impeller. So these are the large vortices. This is where you are going to inject energy into the system. And these big vortices are going to break down into smaller and smaller eddies. And when you reach very small eddies, then the viscosity is efficient and is going to dissipate the energy because, of course, you reach at some point a steady state. You feed the system with energy due to the impeller. At some point, the flow is almost steady. So it means that all the energy which is coming in has to be dissipated. And it is dissipated by viscous effect at the very small scales. And it is actually dissipated by the very well-known effect, Joule effect, which is due to friction. Okay, so if you slide your fingers on the table, you know that it's going to hit your fingers. And this is the same in a fluid. In a fluid, you have shear. So let's say a turbulent flow is composed of eddies. If you make a zoom here, it's actually a shear flow. And here you see that you have sliding fluids elements, and these sliding fluids elements are going to have friction, to experience friction. And because of friction, you have Joule effect, which is going to dissipate energy into heat. So actually, if you do measurements of the temperature within a turbulent flow, you will see fluctuations of temperature, but at very small amplitude, like 0.001 degree, because you are not going to heat your system just by making turbulence. But if the turbulence is very intense, then you can hit the system. Okay, so you can hit the system just because you inject energy, you inject mechanical energy, which is going to be transferred towards the very small scales, and these small scales are going to dissipate energy by friction, by heat release. Okay? So it will dissipate a lot of energy, and you can see many length scales. So you have the big vortices related to the size of your container, the size of your process, the size of the impeller, and then the smallest scales, which are going to dissipate energy, are very small. And in between, you have many sizes of vortices. Okay, and these vortices are what is called vorticity tubes, and this is what you see here. Okay, all these tubes are actually very intense vortices, like I told you, like the spaghettis in the pasta sauce. Of course, it is very efficient for mixing, so this is why turbulence is present everywhere in industrial processes, whatever the application, because you need to mix, you need to enhance the transfer, and then turbulence is very efficient to do that. Okay, so the theory of turbulence is quite complex, so I'm not going to go into details because that will take me, I don't know, 5 or 6 hours to explain you what is turbulence and how can we understand the physics of turbulence. So I'm just giving you the basics. So the basics are: the large scale is going to fix the rate of dissipation. Okay, as I told you, The large scale is the size of your impeller. Your impeller, you inject some mechanical energy because you have a motor which is driving your impeller, so you know how much energy you give to the system. Okay? So the large scales are going to fix the rate of dissipation. Okay? Epsilon is the rate of dissipation of energy. Then this energy is given to the system as a big vortex. This big vortex is going to break down into smaller eddies, smaller and smaller and smaller. And when you get to very small eddies, then friction is efficient. Okay, so for all these small eddies, when you get a shear, then dissipation is efficient, viscosity effect is efficient, and it is going to dissipate the input of energy because you reach a steady state. So all the energy which is coming in has to be dissipated by friction in the fluid. And then based on this, epsilon, so you know the rate of dissipation, you know the viscosity of your fluid, if it's water, if it's oil, and then based on that, just by dimensional analysis, you can define a scale, which is called the Kolmogorov scale, because this is the guy who got this brilliant idea in the 40s. Because you have a rate of dissipation and the viscosity, you can define a scale which will be the scale of the smallest eddies in your turbulent flow, which are responsible of dissipation. Okay, just by dimensional analysis. Okay, I mean, if you take the dimension, the units, if you take the units of epsilon and viscosity, you can build only a scale, one length scale, and this is the one. So actually,
how small is that eddy?
It depends on epsilon. You see?
Depends on epsilon.
Yeah, you see, if you take water here, it will depend on epsilon. So epsilon is typically 10 to the minus something, 10 to the minus 6, 10 to the minus 8. So in a classic, let's say, industrial flow, epsilon eta can be from few hundreds of microns to few millimeters, because it depends, it depends on the size of your system. It depends on the feeding of energy that you give to the system. But typically, if you take an impeller in a batch of 1 meter, then it will be few millimeters.
How do I know the rate of decay, that is from origin to that stage?
So it is given by this.
Oh, okay.
It is given by this. So actually, this is the work of Kolmogorov between 41 and 42. Yes. So you had a question?
Yes, sir. Actually, sir, this length scale is having the relationship with some Reynolds number.
No.
Because this.
Please repeat the question for the audience.
Yeah, I will.
1/4, they have differentiate with this, because when there is some kinds of turbulence, but that is the low Reynolds number turbulence, that this Kolmogorov length scale, they have the different value rather than this.
Yeah. Okay. So the question is, does this Kolmogorov length scale is depending on Reynolds number? In the theory, so the answer is no. In the theory of Kolmogorov, it has been established for very high Reynolds number flows. So in the regime of very high Reynolds number flow, there is no Reynolds number dependence of the Kolmogorov scale. If you come to a turbulent flow which is not very intense, so you are outside the assumptions of Kolmogorov, and then of course the size of the vortices will be different from this theoretical estimate, but for moderate Reynolds number flow. What I'm talking about, the Kolmogorov theory, is for very strong turbulence, very strong, very high Reynolds number. And in that case, there's no more dependence on the Reynolds number. So you go from the very large scale, L, to the very small scales, Kolmogorov scales, through a cascade of energy. And the rate of transfer of energy is governed by a law which is called the energy cascade, and it has been also proposed by Kolmogorov. And this is the rate of transfer of energy from the large scale to the small scale. So here it's written with wave numbers, but it's just the opposite, just the inverse of length scale. Okay, so K is just something which is proportional to 1 over the length scale. Okay, so it's a wave number instead. It's like if you have frequency instead of periods. You take wave numbers instead of length. So the rate of transfer is k minus 5/3, so it's one of the strongest results of the theory of Kolmogorov, and it gives you the way the energy is given from the large to the very small vortices. Okay, so you have to keep in mind for what I'm going to explain later that a turbulent flow is composed of many vortices. The biggest ones are controlled by your system. It depends on the size of your impeller. It depends on the size of your container. And the smallest ones are driven by the rate of energy dissipation and, of course, the viscosity of the fluid that you use in your system. And then in between, you have many vortices of different sizes that are going to just transfer the energy from the large to the small, and the small scales are going to dissipate the energy. Okay? So this is the picture you have to keep in mind. And of course, all this flow is 3D and unsteady. Okay? All these vortices like this, all these vortices are moving in very complex dynamics. So the question for the particles is, if you place a particle into that very complex flow, what will be the response? Okay, if you have particles, do you observe this dispersion? So they are going to be, evenly dispersed into the flow, or are they going to accumulate somewhere? So we need to know when you have, let's say, so this is a typical turbulent flow. So it's a picture of a jet. So you have fluid coming from the left to the right, and you have a jet. And this jet here is laminar, and you see that progressively you observe turbulence. Okay, so you see many vortices of different sizes. Okay, and the question is now, if I inject some particles here, what will be the response of the particles? What will be the effect of that turbulent flow on the particles? So we need to know within all these length scales, from the large to the intermediate to the very small scales, what will be the ones which are efficient regarding the particle trajectories. Okay? So what is the characteristic time scale for the particle for the dispersed phase, and what will be its relation with all these different scales, from the large to the energetic to the dissipative small scales? What will be important for the particle trajectory? So yesterday we have seen that to characterize the response of one particle, there is actually only one time scale, which is the tau p. So I call it tau r, but it's the same, tau p. Tau p is a time scale over which a particle will respond to any perturbation. Okay, so let's say that you have a particle in the flow. If tau p is very small, then it will follow all the perturbation into the turbulent flow. If tau p is very large, it means that you have fluctuation of the flow, but actually the particle is so inertial that it will move without any interaction with the flow. Okay, so these are the two extremes. Small tau p, you respond immediately to all the perturbations. Large tau p, you don't care about the flow and you move as a bullet. Okay. So we have to compare that response time to the time scales of the turbulent flow. And because we have many time scales in the turbulent flow, because we have many sizes of eddies, we may have different responses to different size of vortices. Okay, so this is what is proposed here. What is proposed here is to build a dimensionless number to analyze the response of the particle to a turbulent flow. And this dimensionless number is called the Stokes number. Okay, so ST is the Stokes number. And the Stokes number is the ratio between two time scales because it is dimensionless. Okay, so it is the ratio between tau p and, let's say, tau f. Okay, so this is the fluid time scale. Okay, that for now I'm not specifying. So if you have a very simple flow, for example, you have only one vortex, okay, of a typical size RF with a typical velocity UF. Okay, so when you have one scale, it's easy because you can define the time scale. So tau f will be UF tau f equal to RF. Okay, so this is velocity, time, so velocity multiplied by time, so this is meter per second multiplied by second, and this is meter. Okay, so you can define tau f as RF over UF. Okay, this is when you have one single vortex. Okay, so in a turbulent flow you have many. Okay, so you have many vortices. You can define vortices and timescales for these large vortices. You can define vortices in the range of in between the large and the small, or you can take the smallest one. Okay, so the Stokes number is going to compare the timescale of the particle to one typical timescale. And in a turbulent flow, what we do very often is to use the Kolmogorov timescale. So you see it's you can define from that definition eta, which is the length. You can define the time, and this time is also just related to the viscosity of your fluid and the rate of dissipation, the rate of energy consumption in your system. Okay, so you can define this Stokes number, and depending on the value of that Stokes number, you will have different response. Okay, so I just remind you what are the different response that you can get. So you have three regimes. Stokes number much lower than 1, Stokes number order unity, and Stokes number much larger than 1. Okay? So what do you think? For Stokes number much lower than 1, what do you expect? You have a turbulent flow, and you have a Stokes number which is much lower than 1. You feed the system with particles. What do you expect? Are they going to be dispersed? Are they going to accumulate? What is your feeling? Yeah, it will be dispersed, okay? Because when the Stokes number is very low, then the particles are following the flow fluctuations. Okay, and in that case, you have dispersion. Okay, so because the time scale of the particle is very small compared to the time scale of your flow, if you seed the flow with some particles, they are going to follow all the perturbations, and then they are going to be dispersed everywhere. Okay. So now, if we come to the extreme in terms of Stokes number, when it's very high, in that case, tau p is much larger than tau f. So it means if you seed the particle into the flow, they are not going to feel the effect of the flow. Okay, so they are just going to sit where you seed them, or they are going to have very simple trajectory, like if you take this and you just throw it. So, okay, so the trajectory is not depending of the surrounding flows. Okay, so in that case, particle trajectories are independent, almost independent of the fluid flow. Okay, so when the Stokes number is very large, particles are almost, so not particles, but particle trajectories Okay, so particle trajectories are almost independent of the turbulent flow. Okay, so these are the two extremes, and in between, when Stokes number is of order 1, okay, so it could be 0.5, 1, 2, 3, okay, so of order unity, then you have a strong interaction between the turbulence and the dispersion of particles, okay, and this is what we are going to comment. So in that case, there is a strong interaction between particle trajectories and turbulence. Okay? And this is when the Stokes number is of order 1 that we expect the most interesting physics, because in that case, the particle statistics will be almost the same as the fluid statistics. In that case, the particles' trajectories are nothing to do with the fluid, so there's no interest. And in between, when Stokes number is of order 1, then we will have a strong correlation between the fluid and the particles' motion. Okay? So this is what is given on that map, which has been proposed by Ferrante and Elgobashi. So they split the domain of concentration and Stokes number into different categories where you may have different response of the particles and on the flow. Okay, so you remember that when we increase the concentration, we move from one-way to two-way to three-way to four-way coupling because of the particles' interaction with themselves and with the flow. Okay, so as you increase the concentration, you will move from one-way coupling, fluid effect on particle, two-way coupling, fluid effect on particle, but also particle on fluid, to four-way coupling, the same but with also collisions and hydrodynamic interaction. Okay, and here you increase the Stokes number from very low, so actually you have very small particles, very reactive to the flow, to very high Reynolds number, where you have bullets which are just throwing, moving through the fluid without any interaction. Okay, and yeah, sure. This is concentration, so it's the value of the volume of the particles divided by the volume of your system. Okay. Okay, so let's say if you have NP particles, okay, so if your system is V, this is the volume of your container, you have NP particle into that system of all the particles, let's say, are same size, same radius, R. So this is the volume of the particle, all the particles divided by the volume of the system. Okay, so it goes from 0 when it's very dilute to 60% when you have a dense suspension. Okay, so you go from dilute suspensions to dense suspension as you increase the concentration, and you see that when it's very dispersed, so it's 10 to the minus something, 10 to the minus 6, and when it comes to 10 to the minus 2, 10 to the minus 1, then particles are going to interact. Okay. And then you have here the effect of particles on the flow. Okay, so when you have very dispersed suspension, there is no effect on turbulence. And then when you have dense suspension or moderately dense suspension, you may have an effect, and it is specifically difficult to predict when the Stokes number is of order unity. So you see when here you are in between 10 to the between 1 and 10 to the power 2. Okay, so now we are going to look at what is the specific effect of one vortex on particle trajectories. Because if we are able to understand what is the effect of one single vortex on the particle trajectory, maybe we can have an idea of what will happen to that trajectory within a complex turbulent flow, because it is composed of eddies. So if we understand what is going on with one particle, one vortex, maybe we can have some ideas about what is going on when you have many eddies, many particles. Okay? Yes?
We hear vortex and eddies. Can you just?
No, it's the same for me.
Okay.
Vortex and eddies is the same. This is it. So it's a vortex and an eddy. An eddy is the same for me. Okay, so we are going to do a simple problem, which is I take a vortex and I place a particle into that vortex, and I would like to know what will be the response of that particle to this specific flow. Okay. So what is your expectation? What do you think? What will be the response of that particle into the vortex? For now, I just assume that G is I'm not considering the effect of G. We will see later what is the effect of G, but for now, I'm not considering the settling velocity. So I just have, let's say, the horizontal vortex with a particle. So what is your expectation? What the particles are doing?
The particle is outside the boundary of vortex.
No, it is inside the vortex. Inside the vortex. So it will, yeah, the particle is going to rotate with the fluid. Okay, so we agree with that. Okay, so the particle, due to the flow, due to the drag, is going to have a trajectory which is almost like this. But the question is, can we predict if the particle is going toward the center of the vortex, or is it going outward? Is it going to be expelled outside the vortex? So outside, okay? So you think outside. Is it always the case? Is there a criterion for which you know if it is going inside or outside?
Velocity and distance.
No.
Inside.
Inside. So why is it going inside?
Because there is strong centrifugal force toward the center. Centrifugal force goes out.
Yeah, exactly. So the centrifugal force is going outside. So why? So under which conditions can we have particles going inside the vortex?
When the radial force is much more dominating towards the center.
Yeah, but why? Which force is going to drive the particles toward the center of the vortex?
The drag force is more than the
Okay, so you have the choice.
Drag force.
The lift, I guess.
Yeah, it could be the lift, but actually it's not. It's actually that one.
Oh.
Okay. This one is going to drive the particle. So we can have a look if you want. We can take a very simple vortex. Okay, so I take a very simple vortex. I'm going to give you the analytic expression. It's called pure rotation. So it means it's a fluid which is just rotating, like this. Okay, so it's what is called a force vortex. So so if I call it x and y, the flow velocity has two components, u, v. So u is minus gamma y, and V is plus gamma x. Okay, so you see, for example, when you are on this axis, so you are at y equal to 0, so u equal to 0, and v is gamma x, so v is increasing like x, so this is what I draw here, so the flow velocity is moving up. When I am on this axis, x equal to 0, so there's no v component, only u component, and it's minus y proportional to gamma. Okay, so it's minus y, it's going on the left. Okay, so this is a flow which is pure rotation. So the fluid is just rotating like a solid body. Okay, so now I'm going to place a particle into that rotation, and I'm going to look at the different forces. Okay, to see if the particle is going to move inward or outward of the vortex. Okay, so if I take the du by dt, so the added mass force. So if I look at du by dt, so you have du by dt plus u scalar gradient of u. Okay. So this flow, you see, is not depending on time. Okay, so it's a steady flow. So because the flow is steady, du by dt is 0. Okay, and now we have to compute this this term. So u scalar gradient of u has two components. So it's u du by dx plus v du by dy. There's no w. Okay, w is 0, so there's no w. And then you have u dv by dx plus v dv by dy, and this is 0 because w is equal to 0. Okay, so that term corresponds to this. Okay, so I'm going to compute that based on that flow field. Okay, so that will be u, so u is minus gamma y multiplied by du by dx, and du by dx is 0 because it doesn't depend on x. Okay, so multiplied by 0, so this is 0. V is gamma x multiplied by du by dy, and du by dy is simple because just have to make the derivation over y, so it's minus gamma. Okay, so multiply by minus gamma. So I do the same here. So u is minus gamma y multiplied by dv by dx, and dv by dx is gamma. Okay, v plus gamma x multiplied by dv by dy, but v is only a function of x, so dv by dy is 0. Okay, so it is 0. So finally, what we get is the added mass force is minus gamma multiplied by x, so it's minus gamma square x, and minus gamma square y, minus gamma square y, and 0. Okay, you all agree? Okay, so just have to take my flow field, analytic flow field of pure rotation, and I just compute the u scalar gradient of u. Okay, so now we have the expression of that force. We have the expression of that force, okay, du by dt. So, can you tell me what is the direction of that force? Okay, so this is how this force is pushing the particle. Okay, so let's say the particle is here. How this force is orientated? Is it like this, like this, like this, like this, like this? Okay, it is like this, because here you see we are in a quadrant where x is positive, y is positive, x is positive, y is positive, so with the minus, both are negative. Okay, so you see that the components are all negative, both components are negative, so the force is acting like this. You all agree? Yes? Okay, x is positive, y is positive, because we are here. This is x and y positive, here, all over here. And the component of the force are minus, minus. Gamma square is, of course, positive. X is positive, y is positive, this is positive, and minus, minus is, of course, negative. Okay, so minus, minus is negative like this, negative like that. So the force is like this. Okay, so now if I take the particle at another location, because the particle is going to rotate, okay, so it may be at any location. So if I have a particle here, then y is positive, x is negative. Okay, so y positive means that this force will be negative, this component will be negative, and x is negative, so with the minus it will be positive, so it will be like this. So these are the two components, so the force is like this. Okay, so now I take one here. So here x is positive, so that will be negative, it will be like this. Y is negative, so that will be positive. Okay, so that will be like this, so the force is like this. And the last one, here we have x and y negative, x and y negative, sign minus, minus, so it will be all positive. So positive, positive, so the force is acting like this. Okay, so you see that whichever the position of the particle within that vortex, the added mass effect is going always to push the particle toward the center. Okay? And on all these forces, which is the one which is pushing the particle outward? So which one? Okay, so this one, added mass, is going to push the particle toward the center. And which one is pushing the particle outward? Sorry? No, not the lift.
Drag.
Not the drag. No, the drag is only because the drag is always along. No, there's no G. There's no gravity. So there's no G. Yeah. So where is the centrifugal force? Exactly. So the good answer is the centrifugal force. But where is it? Where is that force?
In FG we can convert it.
Sorry?
In FG. It's the gravitational value.
No, there's no gravity. There's no gravity.
But omega term is in FH.
So where is the centrifugal force?
Outward.
Yeah, it is moving outwards, but where is it in the equation? Where is the centrifugal force?
I don't think we can split.
It is somewhere. Yeah, so what do you propose? Yeah, tell it. Exactly. So the centrifugal force is here. It's actually in the acceleration of the particle. Okay? Mp dv by dt. If you, because the velocity, so the velocity of the particle will be, so it is rotating like this. So the particle velocity will be like this. Okay? It will be oriented like this. If you take the derivative of that, you will see that there is a component which is like that. Okay? So the inertial force is not a real force. Okay? It's not a physical contact which is generating that force. It's just a force because the trajectory is not straight. It's just because you have a curve. Okay? When you are in a car and you take a roundabout, you go outward, but no one is going to push on your hand. It's just because you change the trajectory and you have inertia. So inertia is not a real force. It's just when you have a curve, curved streamlines or a curved trajectory, and it's included into the acceleration of the particle. Okay, so the centrifugal force is actually in that force. And you see that this centrifugal effect is proportional to MP. This added mass effect is proportional to MF because it is multiplied by the density of the fluid. So now we can have the condition for which we have centrifugal effect, so the particles are going outward, or if the particle is going inward. So what is the condition? It has to be related to the mass of the particle or the mass of the fluid. If the mass of the fluid, the mass of your particle is larger than the mass of the fluid element, then centrifugal effect is going to win, and then the particle is going outward. Okay, so if rho p is larger than rho f, then the particles are going outward. If rho p is lower than rho f, then the particles are moving inward. Okay? So this is a very important result. Okay, so let's say, so the summary is added mass effect is always centripetal, okay, which means towards the center. And this effect is proportional to rho f, okay? Inertia, so this is just mp dv by dt, is always going to centrifuge the particle, centrifugal, okay, toward so it's outwards. Okay, and this one is proportional to rho p. So the condition for the particles to move inward or outward is if rho p is larger than rho f, then the trajectory will be like this. Okay, so the particle is going outward of the vortex. It is spiraling, but outward. If rho p is lower than rho f, then the trajectory, maybe the vortex we took was rotating in the other side, in the other direction, so I'm going to make it. So the vortex is like this, vortex is like this. So the trajectory in that case is going to rotate like this. Okay, and for particles which are less dense than the fluid, then they are going to rotate like this. Okay? So this is the case, rho p larger than rho f. So this is the case for particles, drops in gas. This is the case for particles in liquid. Okay, if you take particles that are denser and generally than water. And this is the case for bubbles or for oil drops in water. Okay, generally oil is less dense than water. Okay, so you see that if you have particles denser than the fluid, like particles drops in gas or particles in liquid, they will be moving outside the vortex. And in the case of you have light particles, less dense than the fluid, then they are going to move toward the center. Okay, and you see that the difference is very different. The difference is very drastic, because if you have a turbulent flow, you have many vortex now, many vortices. So you expect that if you have particles denser than the fluid, they are going to accumulate outside all the vortices. And if you have bubbles, they are going to accumulate inside the vortices. And it is actually a way, I don't know if you can test that in your bath tube. Okay, so you have your water, you generate turbulence, okay, so you mix, and you will see that the bubbles are going to collect within filaments. And these filaments are actually the vortices. So it's a way, because of course if you take a cube of water, you shake it, you are not going to see anything inside. You know that you have turbulence, but you cannot see the turbulence because it's completely transparent. So a way to visualize the vortices is to inject small tiny bubbles. Okay, and these tiny bubbles are going to collect inside inside these spaghettis. Okay, and these are the vortices, the strong vortices, the vortex tubes. Okay, so if you do this experiment, you generate turbulence, you will see some bubbles, and these bubbles are going to spiral inside the vortices. Okay, so the question now, we have understood what is the behavior of particles and bubbles in turbulence. So we have to know, we have to look at many particles now. Okay, so we are going to make a 5-minute break, and then we come back for the case of many particles.